Hello, everybody. In this lecture, we shall find the coefficients of a linear regression line by using OLS method, ordinary least square method. We shall do the same and find the coefficients of the same data set by using the gradient descent method. After finishing with Python, we shall move and solve also the same problem by using LabVIEW. So let us begin. The data set is given as a dictionary, as you see here, between these two brackets. We convert it to a data frame by using pandas data frame function. And the data frame, if we print it as shown here, we shall see a table with label here hours, another label score. This is the set of values which represent the independent variable, and this is the other set of variables or dependent variables. This is indexing values of the table of the data frame. This is the shape of the data frame of Python. In order to work with the OLS, we have to import statsmodels.api, and we import it as SM. We shorten the name to be SM. When we call it, we shall use SM instead of statsmodels. And we imported pandas, as you see, because we have used the function of pandas data frame. Pandas is a library of Python. It is a very strong library which is very widely used in machine learning. Data frames is a way of coding data, and this way gives facility to minimize the occupied memory in the computer. So now we have the dictionary, as you see here, with the K hours and another K called scores. This represents the hours used by the student in studying a specific subject, and the score is the achieved score depending on the value of spent hours in study. So there is a correlation between the independent variable, which is the hours, and the dependent variable, which is the scores. And we want to find this correlation through linear regression activity. Okay, in order to have the value of X value, or the independent values, we extract the hours from the data frame. As you see, X1 or DF, we extract the hours and assign these values to a variable called X1. If we want to see the dependent variable, we also extract the other score K from the data frame, and we get the values of Y. To have a scatter plot, we use PLT function, library, PLT dot, we call the scatter function, and pass there the values of x, x1 here it is called, and y, and then we will have the scatter plot as you see here in blue, these points which represent the scatter plot. Now we have plotted the scatter plot. What is left to do here? We need, as we have said before, we need always, when working with the OLS, to use a very important and essential statement, which is add constant function. So from SM, which is stats models, we call the attribute or the function add constant of x and assign it to x. If we print it, we shall see two columns, one of them representing the values of x and the other column which is values of ones. If you look at it, here it is. Here's the value of the independent variables from 1 up to 15. And against each value, you have one value as a constant. This is the result of add sum or add constant of x. Having done this, what we have to do now, only to call the OLS function. So from SM, we call OLS function. We pass there the dependent and independent variables. And from it, we call the function, this is its built-in function, fit function, dot fit function. Now, we have realized the linear regression model. In order to watch the summary, we call the model, and from the model, we call summary function. The summary function really is very comprehensive here. It includes a lot of information by using different statistical methods. But the most important thing which we need here from the summary is really the regression coefficients. So as a result of printing the summary of this model, we shall have this table, which is given here. This table is the reflects the summary. And as I explained in the previous lecture, this summary, as you see, is very, very detailed. It is really very rich and may be used for other machine learning purposes. But if you look at the first block here from the upper side to the left, you shall see a descriptive data to the same OLS function as the what is the dependent variable there. It is the scores, as you see, which represents y, for example. And what is the model itself? It is ordinary least square model method or model. The method is least squares. The date, the time, and the number of observations, the number of points here, which is 15 points, for example. The real 15 points, which were used 13 of 15. Another really important here information given is the R squared value, which represents the accuracy and the consistency of the results. Here the accuracy is 0.823. The coefficients, here they are. One of them is the slope, 1.77, and the other value represents the intercept value. If we look at the figure, we shall see here, this is the regression line, as you see, and the values are given as you have seen here, and everything is okay. How we have built or drawn the line, we used NumPy to find the maximum value of x, the x independent variable. It has a maximum value, we found it. It has a minimum value, NPy dot minimum, we found it. Now we have the maximum and minimum, the range. So we can define the step which we are going to use. And by using an NumPy also, we can create an array called x0. This x0 represents the axis values, the x-axis values, and this x-axis values now could be used in the equation of the linear regression line. Why? Because the linear regression coefficients now are known to us. Here they are. So x will be multiplied by 1.7735 is the slope plus 66. This is the equation here, as you see here. This is x0 multiplied by the slope plus 66 gives you y. Now we know for every value of x, we have a corresponding value of y. So we can plot y, giving it a color, red color, and then we can have the plot of the linear regression line, which is shown in red, as you see here. Of course, if you want to find any specific value, as I have illustrated here, for example, for the value of 10, what is there? You have to multiply the x0 value of 10 multiplied by the slope and add it to the constant value, which represents the intercept. It will give you the output or the dependent variable, which is the score in our case. So we have, as you see very quickly and easily, can use the ordinary least squares method directly, and we can find the coefficients, and we can have some estimation of the accuracy of this method as it is given through the R-squared value. And as you see, the problem is solved. Now we shall try to do the same by using Python, but with the gradient descent method. We shall do the same. We shall use the same dependent y values and the same x independent values. This is important here so that we can compare between the results of using gradient descent and the results which we have achieved by using the OLS method. Okay, in order to plot the regression line here, we have imported matplotlib, and in order to manage the arrays, we have imported NumPy as NP. Initially, as you see, we have defined the value, one value of the slope m current. It is given a value, initial value 0, and the b value, which is also the constant intercept value, it is given a 0 value. So we have initialized the values of the slope and the value of the intercept by a 0 value. This is what is done. We have also assigned the iterations value. This is a variable iteration. We have assigned to this variable 100,000 values of iterations. y100, I have tried it before, and I found this number is very useful. If you want, we can change it and see the response accordingly. The learning rate in gradient descent here is given, as you see, 0.001. The values, as I said to you, of the independent value are given the same as in the previous example. We have assigned the length of x as a variable n. Really, we know it is 15, but for generality, it is assigned a value of n. Now, we're having the values of x and y. Of course, we can plot the scatter plot of both, but I didn't do it here. I'll do it later downwards. Also, we have created a list here, and this list is assigned to a variable called cost history. The cost history, which represents the history of the objective function and how the minimum values, we shall see later on how the minimum value is changing towards the zero value. To work with this function, we create a for loop for I in range of iterations, which is 100,000. This is the equation of the regression, known, it is linear regression. So m current multiplied by x now known to us. M current is also known to us. It is assigned an initial value 0. And B current is also known to us. So all this combination, linear combination, is assigned to a variable. We call it the prediction output, or y predict. So this is practically the regression line equation. The cost function, as you see, generally, we have met this expression in the first lecture. It is equal -1 divided by n. N is the length, or the number of iterations, the length of x, sum of the squared error, sum of the value squared for value in y minus y predict. Y, this is the true value. Predicted value is the value at the output. They are not equal. There is a difference between them for each point. This is the residual, as we have said before, or the dynamic error. So this error is now squared for each point, and then it is summed. And to find the mean square error, we have divided it by n. This is already known to us. So this is the mean square error, where the residual is y minus y predict. Now we have to find the derivative of the cost function by the variables which are there. Remember, we have decided that the coefficients M current and B current must be considered as variables. So when carrying out the derivative by the slope M and by the B, which is the intercept, yes, we can see these two expressions, and these expressions also were derived to you in the first lecture. So the derivative d of the cost function by the variable m is, as you see, minus 2 divided by n multiplied by the sum of x multiplied by the difference, or the error. 2 here appears because we have here value squared. So when you differentiate it, it comes out here. and minus it is given here. The same expression we got to the derivative of the cost function by b, but without x. So the sum of y minus y predict. Now, having the derivatives, we multiply as usual the derivative with the learning rate. And in order to get the subsequent value of m, we subtract the step value here, which is the product of learning rate by the derivative. We subtract it from the m current value and assign it to a new variable called m current. The same thing we do with the b current, which represents the intercept. The cost history here, which is here, now we append to it the value of the cost for each iteration. Finishing with this now, we are going from up to down, up to the moment when all iterations have been implemented. So if we now get out from the for function here and print m current and print b current and print cost and print I, we can get the last value at the end of iterations when I is equal to 99.999. And yes, and we shall get the value of the cost, and we shall get the values of the coefficients m and b. The current value here will be the last value, which happens at 99,999,999. So now, having these values, we can plot the scatter by using the x and y, which were before. And now we want to plot the line, the regression line. We create an array of x, we call it x1, by using numpy dot arrange a range function between the limits 0 and 15 with a step equal to 1. So we have created an array of values, not more. And now this array of x now is multiplied by the slope, which we have got here, m current. This m current value now is 1.74. And the b current here is also 66.42. And the I number of iterations is 99,999 instead of 100,000, because we began the count with 0, as we have said before. So all the values which are here now are existing at the last value. This is the number of I iterations. This is the value of the cost function here for this case. This is the value of the intercept, and this is the value of the slope. So we take the value of the slope, 1.74, multiply it by the array x here, and add to it the constant intercept value. We can find the y, or the dependent predicted value. To plot it, we just call the PLT plot, x minus 1, y minus 1 here. We can give it a color equal to red, and then we shall have this line which represents our case. When using gradient descent, we can see the cost function and how the cost changes, the error, how it changes, depending on the value of the iteration. So here we are using PLT plot. This is the number of iterations, range number of iterations. We shall put the cost history with a color red, line width equal 0.5, and it is given a marker as asterisk. If you look at it, you remember how it looks. This is the asterisk and begins with a very high error value, and down quickly, very quickly, it converges to the minimum value, which is given here, which is minus 11.039 here. It is not seen here. You cannot see it because the scale here is very large. Yeah, but it shows the character really, and how the gradient descent works well, and how really it converts to a minimum value where the error is a minimum value, where we get at this point the value of the intercept 66.4 and the value of the slope of the function. So as you see, the number or the value of the intercept here, 66.4, and the value of the slope are exactly the same values which we have got when we used the OLS method. There is no different. If you go back, here it is 66.33. Here in the gradient descent, it is 66.4. No difference practically. And there 1.746. And there it is, here it is 1.7734 instead of 4. It is the same. So practically, we have achieved the same results by using the gradient descent or by using OLS. Now, which of them is easier for you to use? This is, or the OLS is more systematic for use really, and it doesn't require from you detailed and to remember different steps which we have done by using the gradient descent, but it depends on your flavor. You can use either this method or this method, and we shall see later on, maybe through one lecture, we shall see how we shall use the SciPy for the same work, and how really we can get even more easier way to find the coefficients of linear regression. Okay, this is the two ways of finding the linear regression, which I wanted to demonstrate with you by using Python. Now I shall go to LabVIEW and show you also how we can solve the same question, the same problem, by using specific methods also used for optimization, for regression in LabVIEW. So the first one of them I shall demonstrate to you is example 9-1. This example also includes the same dependent and independent variables. They are shown here as arrays, of course. They should be shown as arrays. Here is one of them. This is X, which is an array from 1 to 15, which represents the variables of the dependent variable and the values. And these are the values, the same values which we used by Python for the independent variable. To work here, we have used with LabVIEW, we have used a function, built-in function called Linear Fit.VI, Linear Fit Virtual Instrument. If you right-click here and go to the mathematics and go to fitting, here you will find a number of functions which could be used for regression. One of them is linear fit regression. Of course, the type of the function which you select depends, of course, on the character of distribution of the values of x and y, the positions of x and y on the plane. In another way, the character of the scatter plot. If the scatter plot is close to linear, really it is recommended to use the linear. But it may have an exponential character or a power character or Gaussian distribution character, any different. In LabVIEW, really, they are worked out with very interesting classification, and you can select the virtual instrument here or the method which is the closest to the distribution of the data set. It depends on your, of course, point of view. So now we are considering the linear fit. We take this and put it here. Here it is located. Now it is not needed. I finish with it. To work with it, as you see, it requires some input. Of course, if you don't know it, go to the help. Here the help. And you can see the inputs and you can see the outputs to this virtual instruments. The inputs, this array, as you see, this line a little bit thick. And this line, this is the X dependent variable array. This is the Y dependent. It has to be created here, added here. You can suggest the tolerance you need. The program itself gives you an idea or offers you a value. If it is not appropriate, you can increase it or decrease it. You select the value, the method which you are going to use. This is from the input side. If there is bounds on the parameters, you can have it. If there is no bounds, no problem. At the output here, you will get the slope directly, and you will get the intercept value. But very interesting here with the LabVIEW that also it gives you the values of the best linear fit. The line of regression has a set of predicted value for each input value. This set of predicted values is given to you here also for your use, and it could be used, of course, so that to overlay the plot of the predicted or the Y predicted on the scatter plot. This is maybe the most interesting thing here. So now, with this finished, we go back and see. Here is the X independent variable. It is fed to this input X. Here you see X. And this is Y. It is fed also to the Y. If you double click it, you go back and see what it is. It is this array. This is Y. And this is the array of X. We go back to the block diagram. Now we have here also created a constant and selected the method which we are going to work with. I have selected the least square. If you click on this arrow here, you can select between least absolute residual method or y-square method. Anyhow, I tried both. The three of them, they give the same result. There is no difference practically. Now, at the output here, you get this array, y predicted array. The best linear fit values. Of course, if you want to see it, I have taken it here and I created an indicator here. If I double click it here, you see these values. So now instead of 64, for example, you have 68 dot and 66, 69, and you continue, and all these values are the predicted values instead of these real values. So as you see, there is differences, of course, between them. And because these values are the red values on the plot here, and these values are the values which exist on the line of regression, which is in white here. But if you look at the line of regression coefficients, you will see that the slope is 1.74 and the intercept is 66.4, which is really very close to the values which we have found by using Python OLS or by using Python gradient descent. Concerning the accuracy, the R square here is 0.83, and there it was 8.3 0.83, and there it was 0.83. The same accuracy practically we have got in this method by using this method or by using that method. In order to overlay the line of regression over the scatter plot, I go back here and show you. So as you see, first of all, I plot the scatter plot, which is the dependency between x and y. This is the value of x, as you see. This is x value. Here it is to the bundle. It is fit to the bundle. And this is the value of y, which is, here it is. This is x and this is y. No, it is not. I have, again, this is the output, which is y predict. And this is the x. So at the output here, we get this cluster, as you see here. Now x and y, this is x coming to this bundle, and y here, it is coming here. At the output, we have this cluster. This cluster, if you plot it alone, you will get the scatter plot. But I didn't want to have it alone. I want to overlay it with the linear intercept. So I take this cluster, and the cluster, which is composed from the same x values, and the output of the predicted values here, the predicted values and the x values. Now I have two data sets or two clusters. One cluster, which is x and y, which are the scatter plot. The other one is x, the same x, and y predicted, which is the line which we have seen before. I make an array. I build an array by using both cluster. This is a cluster of arrays, and display it on the XY plot here. So this plot here now contains the Y predicted values and the scatter plot, which is the initial setup of the data set. If I run it, nothing will change. You will have the same values here. Well, okay. Is there a difference between LabVIEW and Python? I cannot say that there is any difference. We have got practically the same answers. The way we are working is the same analogy. You need to have an array of X, an array of Y, and you need to overlay both. You can do that on each other. And there is nothing new. They are equivalent in their results. Okay, but I have really, this is, if we go back, I have tried this by using Linear Fit.VI. If we go, let us go from this and show you another example I have used it in LabVIEW, which is this example. Now, this is very close, very similar to the OLS function. If we go to the log diagram and see what is there, let me make it bigger for you. We have used here a function called General Linear Fit.VI. This is not exactly the same which we have used before. Look, if we go back to the mathematics and go to fittings, we shall see here the linear fit which we have used before. This is the function which we have used, but there is another function here called General Linear Fit. This one, General Linear Fit.VI. This is the VI which is used here. Look, it is the same, the general fit. But this VI is very appropriate that it shows you how we can create or use the add constant of x which we have done before. In LabVIEW, this is manifested here as this array which includes a column of the x values. Here the x values 1, 2, 3, 4 up to 15. I have shown 4 only because there is no need to show all the values. And the other column of ones. This is called here the h function. I have written here for you. Using Python ordinary least squares, the results are 65.33, 1.77. You remember, we have seen it there. Now, if you want to compare these results which we have got when using OLS with the method here, well, here it is 66.4 instead of 65.3, and it is 1.7, sorry, it is, yes, 1.75, here it was 1.77. The accuracy, as you see here, 0.837, there it was 0.834. So according to the results, no serious difference. The same results practically we are achieving here. So we can use this value, and we can use this value and write the equation of the linear fit, because in order to write the expression of a line, you need only 2 points. This figure here represents the overlaid linear regression on the data set itself. And as you see here, the values are the same, the x values from 0 to 15, and the values here also from 0 to about 90, 98, about 93. Here it is 95, the highest possible value there. So, in general, let us go back. We have here used another function, which is the general linear fit.VI instead of the fit.VI which we used before. But this requires from you to create the H matrix, which is the analogy to the add constant of x. You remember. So this is done here. We take x1, this is the y dependent variables, and of course you can go up and see from the beginning, and this is the x independent values, and now as you see the y is fed to this function as required. It is required to be fed here, but instead of x here you need to input the H matrix, which is practically representing the result which we have seen with Python. How to make it here? We have first used this, as you see, array, we have found the size of the array. Now it is given here. And we have initialized array. If you remember ones, we have added ones there. So it is better to take it away from here. It is given here. And both of them are used to build an array. This is an array. Why it is there? Build array. It is an array. So the output now, as you see here, we have an array, we have an array. As output, we have two-dimensional array, one of them for ones, the other one for the x's. We transpose the array here and feed it to the general linear Fit.VI. This is what has been done. Now at the output, we shall get the result, which is the best fit. Here, if I right click here, sorry, create indicator, and now I go there and I will put it somewhere to see. Sorry, I put it here, and now I drag it and I run the program now. You shall see all the values of the Y predict array. I didn't show it to you because it is not, all these values are included here on this line. So this line practically is built up by using this array. If I go back, you will see that. You will see that this is the output here. Best fit is taken. And now it is, sorry, we have taken it from here. This is once. And we have taken it here once. Now it is taken here as the input of this build array, as an array, as a second array. And the first array is the Y. And the output will be this Y frame. So let me go back again to show you what is there. We have taken the real predicted array output from here, and we have taken the input real values, Y, here Y predicted. We have fed both of them to the function called goodness of Fit.VI. What is this? If you right-click here and go to mathematics and go to fittings and to advanced curve fitting, here you will find this function, which is the goodness of fitting. So you are applying two arrays, the array Y and the predicted Y, and compare between them and see to which degree they are agreeing with each other. The value is here about dot should be about 0.837, which is also exactly the same value which we have got when using the OLS or when we used the gradient descent. What is interesting here, this is an additional information for you. As I told you, you can use the value of the intercept, which is calculated by the program, and the value of the slope, and directly write the equation of the regression line. Y is equal to B plus mx here plus x2, this is not necessary for generality, but it is 0 now. X2 is 0. So this is the equation of the linear regression line. You can write it directly by hand because you know in advance these values. But if you want to generalize the work and to make it to be written automatically, I have managed here to use a concatenate string function, and then by using the values of all the components, I can get the output here, which is here directly without noticing these values. So this depends on what you want, how you want the things to appear, and to which degree you want the work to be elegant and comprehensive. Yes. So I think here everything, the tolerance here is given, as you see, 0.0001. So I get this R square. If I make my requirements less, and I put it here, for example, 0.001, 1,000, like this. Does this change? I don't think that it will change seriously. Okay, you see, it is exactly the same. I run the program. It doesn't matter because the algorithm which is used here really is very strong and very accurate. Yeah, and very accurate. So to summarize the things for you, as you see, we can realize linear regression up to now by using OLS, Python-based method, or by using gradient descent method. We can find the regression coefficients in both cases, and they were found to be the same. We can plot the regression line over the scatter plot, and we have done that for the OLS, and we have done that for the gradient descent. And also, we have done the same job by using LabVIEW, either by using the General Linear Fit.VI or by using the Linear Fit.VI. When using the General Linear Fit.VI, as you see here, we have to use, or the input here, this input, let me put it for you, for example, this input, which is H, this input H, which represents the add constant of X. This add constant of X is a transposed two-dimensional array, which is composed by two arrays. One of them is the size of the array, which is 1 practically, and the other one, which is the initial values of the array, which is 1, 1, 1, 1, 1. And the last thing here, as I told you, this is an addition work just to write the equation of the linear regression function, which we see automatically by using a program without considering the output values. And also at the end here, we have estimated the accuracy of the work by using the goodness of the Fit.VI. With this, I think everything is clear now. We have finished the second lecture on this type. We shall move forward in the coming couple of days. Thank you for listening, and goodbye.